Welcome everyone. Welcome to this seminar. This seminar is part of a series of seminars we have within MARC. That is this KKS profile that we are running on automation. And we have the pleasure to have here Professor Erik Frisk from Linköping University. Erik will be also the opponent for a thesis, a PhD thesis that is going to be defended tomorrow morning in Kappa by Niklas Persson. Without further ado, I would like to leave the floor to Erik, that is going to speak about something very interesting.
Thank you, Alessandro, and thank you all for being here. The title I chose was Predictive Models for Decision-Making in Multi-Vehicle Scenarios. More or less, this was topic of two PhD theses that we had that finished early 2025. We have continued a little bit on this, so I will outline where we are going. I think I will maybe 30-40 minutes, something like that. But I will start, since not everyone knows, maybe you heard Linköping University, but how does it work? So I will just tell me where I am and where I come from. Very quick. So Linköping University, like here, we are split into several campuses. There is one main campus in Mälardalen. That is where the main, especially that's the main campus. But we have strong presence in Norrköping also. There's also the medical faculty is in the center of Linköping, to the University Hospital. And we also have a small branch at Linköping in Stockholm. There's some artistic woodwork. About 30,000 students, something like this. So it's a pretty, not the biggest, but one of the major universities. So there are, I think, 12 departments at the university, and I belong to the Department of Electrical Engineering. So my background is control, more or less. Although I'm a computer engineer from training. And we have 6 groups or 6 divisions in our department. Computer vision learning systems. That is a group that's growing very, very fast. Fastest growing. My group, nuclear systems. I will tell a little bit more what we do. Information coding, they do quantum cryptology and things like that. Math control, our biggest group. Those are maybe 50 people. Communication systems, very strong group in mobile communication. And then electric circuits and systems, so classical. So many classical. So even though vehicular systems might sound like it belongs in mechanical engineering, maybe we could maybe have done that, but we have a very control-oriented signal processing type of activities. And from the beginning, yes. So the department is around 190 employees, 15 professors in total. 90 students, something like that, plus industrial PhD students that we have quite a bit of. And most of them are in our group. We have too many industrial PhD, I would almost say. I think when I wrote this slide that you have next, I think we have 50-50 on industrial PhD students and academic PhD students. It's nice with these industrial PhDs, but they don't teach. So that's a problem for us. So this is my group. We are 34 employees when we took this picture. 18 PhD students for this group, where 9 are industrial PhDs. And our main collaborators are in the automotive industry due to history reasons, but not all. So Scania, Volvo are very big collaborators for us. Scania is by far the largest. It's very close to Linköping. It's not quite fast to go to Linköping and Södertälje. So that's about the size of the group. If I try to divide what we do in these 6 items. So once we did the combustion control or combustion modeling and things like that. So it's been many years since we did that. So for the last years, I would say this electrification has been a major part of our activities in different aspects. Not only for the vehicle, but also electrification, how the vehicles affect the grid, and like system level analysis and control. batteries, that has been so large in our group that it serves its own spot here. I would say we don't do cells, or we don't manufacture, we don't do electrochemistry in our group that much. We collaborate with Uppsala, for example, for that. But we control them, we supervise them, and we use them in the most efficient way. So that has been very growing, an area that has grown very much in our group. Autonomous systems, that is something that we have been doing for quite some time, and that is one of the areas that I'm active here, and that is most related to Niklas' work. We do not only autonomous systems, autonomous vehicles. We don't have, unfortunately, a self-driving car in our group, so you will see what we do instead. But also we have done vehicle dynamics in different ways and driver behavior modeling for quite some time. And I don't. This is also one part that has been with us for forever. It's fault diagnostics and fault prognostics, fault maintenance, maintenance planning, predictive maintenance. This is also live and well. We also do vehicle propulsion. It used to be combustion engines, now it's typically electric motors and things like that. They kind of connect a little bit here. And I included this optimal energy control because it's often has been the driving force with many of our projects to minimize energy consumption. That has always been behind us. And so this is an application perspective. We have very much a method perspective. I don't want to kill it here, but yeah, I put some numbers in what kind of how our efforts distribute. As you can see, about 50% is on electrification. So this is a big part. So what has happened in our group, it has been diversified quite a bit. So what we do here we have data scientists working. They know very little about the electrochemistry or the battery models that they use here. So it's kind of makes it interesting for that reason. That was very short about where I come from. So I should say also maybe that for me, I'm active in mainly this here and this one here, maybe 50-50, I would say. So I have 2 PhD students here, third one coming in. Here. So what I wanted to talk about for the remaining time here is this project that we did. We wanted to do, when we started looking at autonomous systems, we were kind of interested in, it's a nice area because it's so diverse. You can kind of study its fundamental problems. So this is one of our kind of basic research. We don't foresee that we will be doing applications on things that will be implemented tomorrow. So we are kind of looking at some basic problems that we were interested in. One thing that we were interested in was when we have multi-agent scenarios, where we have a lot of cars driving around, and we want to navigate safely in this environment. And what we wanted to do is to see, can we be more proactive in our decision making so that we don't want to drive as fast as possible through this intersection or through this roundabout. We want to make it as safe as possible. And it would be, how do we study this type of scenarios? And here we have cars and trucks driving about in a highway situation. You could imagine something like this, where we have cars, bicyclists, pedestrians walking about. Maybe they don't follow the traffic rules all the time. Still want to be safe. And we don't want to be safe to the extreme that we kind of are very inefficient in progressing. That is something that we are seeing in our collaborations with Toyota Material Handling, which has high degree of autonomy in their factories. But the autonomous agents, they are safe, but they are very kind of slow. They're much slower than what human would be. So that we want to, of course, increase efficiency, but we don't want to be unsafe. So what these are the people who deserve most of the credit here. Is John, he moved back to China after his work. And Theodore, he both finished in January this year. So mainly Theodore's work I will be presenting here today. This has been together with Björn Olofsson. He's the co-supervisor for this. So both these projects have been funded by something called ELITE. This is collaboration between Linköping and Lund. Very important for us. It's very big funding for us. The new projects that we have are WASP funded. So that is the kind of sources we have for this. But what we try to do is this. So if this is us and we want to navigate in this scenario, maybe we should try to move to the left lane here in the future. It would be good to know what are the intentions of the surrounding vehicles. That would make it easier for us to make a safe decision. If this one maybe is start, it would be good to know what that vehicle is doing. Maybe we don't need to know it on the long horizon, but if you know 3, 4, 5 seconds, have a good idea. And of course, if that one is kind of thinking and going that way, we know a little bit because it has shown its intentions. But if we have, for example, we know that this one is slowing down, that will in turn affect this one. So it becomes kind of complex. How do we get the picture of what will all these vehicles do in the next foreseeable future? So what we wanted to look at, can we model the interactions between the vehicles to better do our predictions of what will happen? And so the interaction was kind of important for us. That is what we wanted to study. We know also that it will be very uncertain. We are predicting the future. We will not know exactly what will happen. And we will know that for sure there will be multimodal uncertainties. We don't know if that one will go that way, straight. Maybe we will suspect that it will go to the left there. Maybe it's starting to drift to the left. But it might go straight also. So there are clearly multiple hypotheses here. And we want to describe that full set of uncertainty. That is what we wanted to do in this project. And we started to look at, and Theodore, we knew from the start that we wanted to explore machine learning approaches to this. When we thought about this, to write down rule-based models for this will be very, very difficult. So let's see. At this time, this was a very hot topic. It's still a very hot topic. But we looked here in the first paper. This was Theodore's first paper in 2021. Then we just looked at lane changes in the highways. How far in advance can we predict accurately a lane change for vehicles? And if you look at, so just look at the globe curve, and this axis here goes the wrong way, so to say. This is the number of seconds until we have a lane change. So here it's 0.1 seconds before the lane change. And at that time, we can know very accurately because it's practically already have performed the lane change. But as you can see, about maybe 2.5 seconds before, we have a pretty strong indication here. Yeah, some quite good accuracy can predict lane changes. And that is 2.5 seconds more that you can use to make it a good decision. That was promising for us. So we started looking at this general problem, assuming that we have some history about the surrounding agents, meaning more or less positions and velocities. Of course, there is a perception problem here that we don't study. We assume that we have kind of GPS positions. You could imagine that everyone is broadcasting their positions and velocities to Wi-Fi or something. Understand that this is an issue, but this is not what we study. But what we want to do is, all vehicles in the scenario, we want to predict what are the possible next few seconds. What do they look like? Can we know that for every vehicle there might be several candidates here, and maybe we want to assign some distribution knowledge to this because we don't know for sure what will happen, and we don't just want to make one prediction. And we also have a problem that the history here, say that we take 3-4 seconds of data. Maybe there's a new car entry. We don't have 4 seconds of data. We only have half a second of data for that one. That we also must handle. So what we really did here, we have tried to assume that we have some information about the road agents or road users. And what we really wanted to study, can we model the interactions? Because we know that someone entering a roundabout and there's cars in the roundabout, of course it has to wait, naturally. So traffic rules. I'm sure there are other approaches, but here we wanted to see. Let's see what we can do with this technology. I want to predict for every vehicle in the scenario, like 5 seconds. See what happens. And there are many high quality data sets available. I will at the end show a little bit what we do, because this has not stopped. More and more data sets, maybe too many. Yeah, and we make the assumption that the perception problem has been solved. That is not what we saw, but recognize that this is a difficult problem. So what Theodore focused on were, we can kind of put it in 4 categories. Here's called differential constraints. We know that cars move in a special way. They don't move like random walks. They move on smooth arcs somehow. Maybe pedestrians don't do that. Bikes, a little bit less so, but still a little bit. You know more than me about that. But we wanted to include that kind of knowledge in our predictions. And that was one thing we wanted. We wanted probabilistic forecasting. We wanted to include uncertainty in our predictions to kind of have an idea how much should I trust this or try to quantify that. The interactions, certainly we want to, that is what motivated us. That was an interesting problem for us. How do you model that? And also, of course, the road network. You don't drive outside the roads. If you're a car, maybe. A bike might. Pedestrian for sure can do that. But so it's not like a hard constraint that it's only this allowed area for prediction. That's not what we want. But we want still people take this into consideration. They generally move in. So if we start with, I will very briefly just mention what we did on the differential constraints here. So we wanted to have, when we are working with control from the beginning, and if you look at motion of cars at moderate speeds, these kind of kinematic models work quite nicely. If we are doing like aggressive maneuvers where you start to have large amount of slip or something, then you need something else, but that is not what we are looking at here. So no avoidance maneuvers or something like that. So we are looking at, okay, can we include such a model in our data-driven approach? So we wanted to include differential constraints at that time, like differential equations. And sometimes we do like orientation-based like kinematic model, but maybe we just do integrators to get it smooth. And if we are pedestrians, maybe we need to learn how they move. So we wanted to be able to evaluate this a little bit. And if you have such a thing in your neural network, it's fairly straightforward. It's not to include it, but you have to have some numerical integration technique. You think of Euler forward, the simplest one that you can imagine. We got high order methods, implicit methods, variable step length methods. All of those are directly applicable here. And we tried a little bit, and you will see in the results that it was kind of important to include these kind of constraints. And it matters a little bit what kind of solver you use or integrator. What we found for this prediction problem that we studied, that these Euler first order methods, they had problems. So, but as soon as you went above that, second order method or third order method, it was fine. It didn't really matter. One thing that we found during this work, I thought this was especially fun. When you train these, but more or less you have a neural network in the right-hand side of your differential equation. And we know that cars are stable. We are not looking at unstable systems. But if you just randomize your weights in your neural network, this will almost certainly be unstable. Not only that, the solver method has a stability region. So we know that, for example, oil forward has a certain stability region, oil backward has a much larger stability region. We realized that, okay, this is an interesting, more or less fundamental topic of training these neural ODs. So we did a ICML paper on that, how we can improve training significantly by considering the solver and the stability regions for that. But it was fairly straightforward, but it mattered a little bit which kind of integration we use. And then for the kind of main part of the work, interactions. So if we look at this, and Theodore was kind of interested in modeling this with graphs. And graph neural networks is a super established technique, but it fitted very well because you have kind of the edges in the graph are where there are interactions. And you can kind of estimate the weight of those interactions. How important are, if you're this vehicle here, it's going to be quite dependent on what happens in front of it, not so much here. So these graphs was kind of excellent tool for modeling interactions. It was also very good because it's in this framework. I don't know if Theodore agrees with me, but for me, it was also very useful because we have this property that a vehicle might enter the horizon or it might leave. So we have very different length of history for each agent. And that was super convenient in the graph neural network. So that works very nicely. So you get like a graph for each time step. And that graph changes with every time step. So for example, here you see this purple vehicle that kind of disappears here because it left. Maybe it took an off ramp and left the scenario, or you have to consider some area around your vehicle. So that was the graph changes over time, and that was the number of nodes is very flexible. That was like that's in this framework. It works directly. So the main model that he did in his, and I won't go into details, is kind of a standard type of approach. So it's like this, if you know this world encoder decoder structure. So you have one part here that kind of tries to figure out the history. What is this scene about? So you have these recurrent neural networks. The only difference what he did was to make it graph neural networks. You have these GRU units, super standard. We made graph GRU. But in any sense, it was kind of standard what he did. Then we have a decoder. This is the predictive part. So now we're trying to predict. This is very similar structure. But so this is one thing that we did. The output of the decoder could have been, and this is what many people do, that they predict the output of the decoder part are the predicted trajectories. But since we wanted to include motion models, we instead output the control signals for the motion model. And we also outputted some uncertainty matrices. It's Q because it's the same Q as we had in like comma filters. So we output not only, so you can maybe see here that there are several outputs here, and there's one for each hypothesis that we have. So if we decide that we want for each vehicle, we want 5 hypotheses, then we have 5 outputs, 5 control signals, 5 uncertainty descriptions. And we also have a mixture coefficient here. So how much belief do we have on each of these hypotheses? And then we integrate them. This is the neural OD part. We integrate this with using the motion models that we have. And those might be these kinematic models, or they might be these neural ODs that we train. And then for the predictive part, we also do the EKF time update step to see how uncertainty propagates over time. And at the end, we get each hypothesis with some uncertainty descriptions. Yeah, so that's worked fairly well. So this was in 2023. So this world, this is ancient, so it will have its due date, but it worked very well. It performed very well compared to its competitors. If you look at the results, what it can look like. So, for example, here you see a scene in a roundabout. You have a number of vehicles, and look at the red one here. So the solid tail there, that is the history that we are putting in. So there are tails. You can see maybe this one. It has practically no tail, but we should still be able to predict the future of that one. You can see the triangles there. That is the predicted. And you can maybe see here on this cyan thing here is that there are one main, and the intensity is due to the belief in that hypothesis. But you can maybe see there are some dots here also that it might continue in this roundabout. We don't know yet. It's too far in the future. But so that is kind of what we wanted. And if you look at this scenario, for example, for the blue car, predictions of that, clearly it should wait for that orange car to pass. That's how people behave. But if you look at our the star there, the yellow star, that's our approach. It predicted that it would stop, and we were not the only one. There are others who did that, but those who didn't really manage to capture the interactions with the surrounding vehicles, they predict that this will just pass, enter the roundabout. That's not great if you are this car and want to predict, kind of plan. How worried should I be that this blue car will enter? Yeah, so that kind of worked. Another thing that we noticed was this. So again, the yellow stars is our model. And this dashed line here, that is the extent of the training, how much data did we include in the training. And you can see that some models really predicted something very weird. And what we could see that our model, and not the only one, all models that included these motion models, they could extrapolate in a nice way. So this was just one example, but we could see that including motion models in predicting vehicle behavior, so very good thing. That is, I think, this neural ODs we have used ever since. Probabilistic forecasting. As I said, we had kind of multiple hypotheses out. So this was classical mixture density network. So you have a mixture of a set of Gaussians or something like that. But simple to formulate, quite nice, but you have to kind of fix the number of densities. You have to fix the type of densities that you're looking at. So what we did, just to experiment a little bit, we did also diffusion models, which is another way to represent these distributions. So then instead of having a fixed set of hypotheses, you can draw samples from a distribution. So sometimes you get a left turn, sometimes you get the right turn, but maybe most of the time you get the left turn, and then that's your main hypothesis. And this is the kind of diffusion process. You can kind of see that it's how it progresses. It was a nice experiment. I think it's very flexible, super flexible. And very slow inference compared to the other ones. So I don't know. This was something that Theodore, he wrote a paper on it. Never managed to send it, and now it's too late. It's just passed. But that is also fascinating about, this is not my world really, this machine learning stuff, but I was kind of surprised that he put it on arXiv when he was finished. I think it had 30 references. It's not even published. So that's the way it is. But it's a nice technique, and I think there are some uses for it as we see it, but maybe not as a part of a planning algorithm. Road network, I will not say that much about it. I mean, we have something like this. This is typically what the map information could look like for a road network. This looks like a graph, so why not use graphs? Because we were fond of them. So we used these GNNs also for those. Just it generalizes very well. We could put in any type of model and a map that we have. And I will show you at the end something we did. Because there are so many data sets that also include maps. It was very easy for us to just enter those in them. But it's kind of expensive. The graph is very dense here. I'm sure you could do a lot here, but so more or less we added one component where we have GNN for representing the graph representing one graph neural network, and just mix everything like machine learning role. So some takeaways from his project. It was quite successful. You can predict the number of seconds in advance, even in quite complicated traffic situations. Highways are very easy. I think you need something, you don't need that this complicated for that. But if you look at intersections, roundabouts, things where you really have to look at and non-signal intersections, it manages quite well. We found that this differential constraints was quite really useful. The trajectories that we predict are smooth and they behave like you would expect, hopefully. It generalizes better than if you don't. Probabilistic forecasting, we use standard techniques that worked. I will come to, we haven't really used it, we just produce a number that we trust this more than that one, okay. The interaction seems to really be captured by this work. It stops when it should, and we have looked at many scenarios and just try to figure out. You can train these models and you get a performance number, negative log likelihood of something, but how do you interpret that? And we have spent some time on having a look at that, and also the road topologies was quite kind of easy to include. So this is kind of where Theodore ended his project. So he did a lot of these predictive models for trajectories. There are two things that we are pursuing now. One thing that, I mean, Theodore did really nice work, but he kind of gets stuck on certain roundabouts or intersections, or and kind of looked deeply into that. But we cannot have an algorithm that only works in one intersection. So we need to really have a look at how does this generalize over different countries, over different roundabouts with different topology, different whatever. So we needed to look at more about the generalization properties of these models. And what we did, the plan was that Jan and Theodore should kind of merge at the end and merge the techniques, because Jan had a more control-oriented approach. I mean, is there any gain on doing this, or should we do something much simpler? I don't know. I think there is something to this, but let's see. So that is why we have two students working on this. Now I will show you, because one of them has started. So one thing that we were interested in, and the number of data sets that are available has grown. I mean, so there come in new data sets all the time. Some major players, some just companies who do things. And what we wanted to look at was a little bit. So this picture here, I will show you what it means. But so these names here are different data sets. This is the Waymo data set. It's a huge data set. This is an old data set from the 90s. They just fixed the camera and recorded highway driving. And this data set, VTH, that is pedestrians. So they are very different. So the question is, one question could be, how similar are these data sets? Because there are interactions in the pedestrians data sets. Is that useful for interaction between cars? Maybe. Or should we not confuse it with that? And these blobs here, that is a 2D representation of the data set distribution. even though these are different variables, so how do we even compare them? So what we did in this work that we are doing now, writing rebuttals at this very day, but we look at 21 of these data sets. So this was kind of a good engineering effort for us. These are 21 data sets. So a few of these top ones here are where there's a static camera filming. Those are typically, it was not made time, it was 2006, but quite some time ago. We have these, typically a much larger size, these data sets, where you have an instrumented vehicle, have data from one vehicle driving around in the city. And all of these here are drone data sets, where they place a drone above some highway or intersection or something and record it. So kind of different, but they are, some are big, some are not that big. And for example, the Waymo data set is by far the largest. Kind of challenging for us to deal with. The new scenes is also another one that is very big. So here we need Veselius, this kind of VASP data center that we use. By no chance we can do this on our own computers. But we wanted to see, here we have, and there are others, but this includes the major ones. What we wanted to see, how do these relate to each other? Because they're not the same. They are very different in how they are collected, but they might still be useful when training these predictive models. So what we did was make something that looks like an autoencoder, but more or less you the data and the network, the road network. More or less, you try to find something in the middle that kind of represents this what we call latent embedding. So some variable that somehow represents. So this is kind of high dimensional. I think this is dimension 128 or something in our example. But we try to find something that, no matter what you put in here, any of these 21 data sets, you get something here in the middle that represents the scenario that you're looking at. This latent variable set, that represents the ego state of the vehicles, or each vehicle, traffic scene and interactions that we have, the history, cars, bikes, pedestrians, try to pick that, static environment, all that should be somehow represented by this variable set. And then we look at the distribution of that variable set. So if we are feeding in here a pedestrian network, then we get some distribution of this variable set. And if we do highway, then we get another distribution of this variable set. And then we compare how do these distributions relate to each other, and how do they, if two distributions overlap, does that mean that it's the same type of information in those two data sets? And that is generally true. And then we get these kind of pictures. So these are, on the right, there are highway data sets. So for example, here we have the US data set. Here's ID is a German data set. XCP is also German. This one I think is Chinese, if I remember. They're not the same, and you can look, why are they not the same? And you can also see, if we go back to this one, yeah, highways and pedestrians are pretty far from each other. Makes sense. And you can stare at these pictures, and I don't include any in this presentation, but what we wanted to see, for example, is A43, that is a subset of ID. Is it the case that if you train on ID, it will automatically perform well on A43? Yeah, it does. So you can kind of easily see that, even though if you look at the data, it's not that immediate why that is. It's also the case that, yeah, you can see a lot of things in this. So that was something that it was interesting for us. We will pursue it a little bit. Let's see what happens with this paper. I want to finish with we don't have any cars. We don't have any. Oh, wait, we don't have any bikes. But what we wanted to do is have something in our lab that we can experiment with. Of course, we can do simulations. And these data sets that we have that are available, they're kind of nice because you can, but these are recorded data. You cannot interact with it. It's just static. So what Theodor did after he finished his PhD, he spent 1 month doing something that he called Sig3 in our lab. So we have a lab where we have, it's 12 by 12 by 12 cube, where we have cameras, like a positioning system. And we can drive around things in there. And what Theodor did was to do something that our objective was that if we had many cars driving around there randomly on that road network, things will happen in intersections that we can't really foresee. So that would be a good test to see, can it navigate in difficult situations. So what he did was, and he wanted to do it in such a way that you could do it in simulation and then easily deploy on these cars that we have. So this is done in ROS. This is the kind of network that he started with. And you can kind of deploy a car, and what it does is to just randomizes a target parking place, and then it drives there. When it comes there, it randomizes a new one, and that is the mission. And you can easily add more and more cars. And all of a sudden, very fast, I would say, 3-4 cars, things, very strange situations happen sooner or later. And the thing is that, yeah, you could add as many as you like. That is nice. That's not so easy in building cars. But this is camera filming from the roof, and this is the simulation, and this is the real. So it's, and the code kind of transfers immediately. You don't have to do anything. And you can also, of course, it's nice that you can, yeah. So in this case, the world has more cars, but in the reality, there's only one, so we have ghost cars. So what we have here, I haven't really used it. We used it in undergraduate teaching, but it illustrates quite nicely that it's very difficult to, by hand, construct difficult cases. They easily appear here very fast. And you can see that you have spent some time on some navigation algorithm. Quite fast it fails because it was something that happened. So it was a nice area. So until we have our own cars, that is, I think, this environment that we will work in. And my last slide. We studied in this project that I talked about predictive models for all users in the scene. So if there are 10 cars in your surroundings, you want to predict all 10 at the same time with the same model, and regardless of how long history you have of each. And the key words is we want to model interactions, we want to include motion models, somehow model the uncertainty, have not yet kind of seen, can we take advantage of that? Roadmaps. And we are now starting to look at how these models generate. And it works kind of nice. Good performance on these data sets. How does this translate to another data set that we haven't seen before, or that is not exactly the same? These are things that we are looking at the moment. And also how to include these predictive models in planners. Thanks.
So we have some time for a couple of questions. I know that Christina had some question, but we needed to leave. But so you will maybe receive an email by Christina. Yes, Mustafa.
Thank you, Erik, for this nice presentation. I have a question. I saw that in your simulation and also in your experiments, there were some situations that 2 cars suddenly reach to the intersection and both stop.
Yeah.
And then suddenly one of them starts to move.
Yeah.
I want to know what is actually the decision-making scenario in this case, and how these cars can understand that the other one will stop and they start moving.
So they have this, see if I remember the word, not decision tree. So he had some logic surrounding the behavior around, say, intersections. So what we had, let's see if I can stop. So in this region, so these were these were like T sections that were like unsignaled. Here we have like this is like a stop sign for wait because you have to stop and then that is what I think you saw here, that two came more or less at the same time and then one started. And he had there is a this logic. If you come from the right, you have I don't know what will happen four at the same time comes.
So it means that somehow the traffic rules are kind of included in decision making.
He tried to he encoded the traffic rules with logic for the simulation.
Because I had this question also about the past forecasting and about the estimation. For example, I think in your neural network simulation that you represented, nothing about traffic regulation is included. But I'm wondering, for example, if you are in front of an intersection and we have a red light ahead, then actually this is very restriction about the estimation of the pass in future. So how we can handle this situation?
I would, if you have knowledge about here is a stop sign, if you have represented that here, then in every data point where you have a stop sign, people will stop. Then I would hope is that the model will pick up on this. But you need to represent that there is a stop sign there. But I think this is highly possible, but we didn't do that.
I meant, for example, the traffic lights, not the stop sign, that sometimes it's green and sometimes it's red.
Yeah, signal, I don't think we have any of those in our. But very good question. We have done a little bit on boats because they have these color rules. So how you're supposed to navigate with respect to each other. Then we have to kind of integrate these rules in the predictive. But that was not the machine learning approach. So, good question. We haven't found a solution for that. It makes sense, but we haven't found it.
Yeah, I have another question related to some of the things that you have here. So whenever you have the prediction of the trajectory of the car, I mean, you have like timing in the position basically of the car over like the intersection, let's say. But then does this affect somehow in a collision avoidance manner the predicted trajectories of the other cars? Meaning that if you know that a car will be in a given position at a given time, will this affect the fact that I want to avoid being in that position at that time? Is this included in the interaction graph, or?
See if I understand. Yeah, kind of, because it predicts everyone at the same time, considering, so it will not predict. I haven't seen it collisions, so it will the predictions that it have will avoid collisions. However, our own vehicle, we know that I want to go there. That is an interesting question. So if I know that, so I know that what I will do, how will then that affect? So the other ones that maybe I don't know, but I know where I want to go. So how do we condition our predictions on? And that is something that we look into. I don't have but it makes sense that we would want to do that.
Yeah. And somehow, I mean, kind of related to this, I know that there was a group at MIT that was by Domitilla Del Vecchio, who was looking into a similar problem where they have like intersections with no traffic lights, and then the idea is to sort of let the vehicles operate as much as they want, like with the driver, but then you want to act only in unsafe situations, basically based on the actual interaction with the other vehicles, and then you want to just not have an autonomous driving, but having an autonomous say safe driver that is a safety net for you. So that was also somehow, I don't know if you are aware of that
No, I mean, this is a frustrating area, but I don't think we will at least continue in this because there are new models like every day. It's really, I feel that it's impossible to keep up. But I've seen a lot of these, but most often it's the other way around. You have autonomous systems where you have a safety fallback, which is typically a more conventional controller. I haven't seen the other way around.
Yeah. Any other questions?
I have another question, which is actually one other part is still a little bit unclear for me. Look, we have a network of cars, and we are actually in the car behind. And our purpose, if I understood correctly, was to estimate the path of the car ahead. So, and we actually, according to your presentation, we use a network, a graph representation of the car in the surrounding of the car ahead, and then based on that, based on the information that we can get, we train a neural network to estimate the path of the car. I want to know that because it's actually how it's possible that a car behind be able to figure out the graph of the connections and the cars in the surrounding of the car in front. Because maybe one car is in blind spot of this car behind, and how it's possible to build such a graph.
I mean, for sure. Let me see if I mean, how do we know where the position of each vehicle? I certainly agree. This is if you think that this is by cameras on that vehicle alone, then we have a lot of problems with the areas.
So we need something.
We cannot think. What I think is this is a real problem. But I would imagine that, say that we have a situation where every autonomous car is broadcast its position and lost it. That makes sense. You have Wi-Fi protocols for that already today. So if everyone did that, that would be enough for us. But if you want to have lidars and cameras figuring this graph out, yeah, it's difficult. I agree. But I actually believe more in this simple broadcasting. That would help a lot.
So we have one more question from online, Sarala.
Yeah. Thank you for the nice talk today. I had this question on the slide 32, which you showed previously. Yeah. So here you said that any type of input is used, and then you get the middle layer, which is the Z. And the Z here represents the encoded layer, right, for each vehicle. And then you try to compare the distribution for different data sets. And you also said that if distribution overlaps, they relate to each other. But what if you said that the inputs are totally different? Is it only that the distributions are compared, and what is the purpose?
So the SED here, it doesn't encode for each vehicle. It encodes a full scene, so a set of vehicles. So it's not one C per vehicle, it's one per scene. And then you can what we looked at here was the distribution, and that is in high dimension, so 128. So here we are projected onto 2D just to be able to plot it. But what we kind of hypothesized is that if the distribution of these encoding SED variables are kind of similar, if our model is sensible, if this makes sense, then all the SEDs here can behave similarly for similar situations. Even though the one is an intersection and one is a roundabout, still, if you have a car coming from the right, you need to stop. That is true in a roundabout. That is also true in this. So that means that we hope, and that is, I mean, how to know, but it looks like that's the SED, that the distribution of SED variables look the same for similar type of scenarios. And if we train us on ID here, then A43 is kind of covered already. That we can see.
So it doesn't matter what features are there in the Z.
The SED is the same for all data sets.
Okay, it's the same features.
Yeah, well, they call it latent, meaning that they
Yeah.
don't know what it is. It's just one.
But the inputs are same. Inputs are same.
The inputs are, the inputs are, you have a graph for the map and you have positions and velocities for all vehicles. That is the same.
Okay, thanks.
Good. So if you have more questions, you're welcome to contact Erik. He will be here tomorrow as well for Niklas defense, not during the defense, hopefully, but he will be around in a little longer than defense. Otherwise, we thank the speaker again. And I wish to see you all at the defense tomorrow.
Thank
Thank
you.
you.
Thank you.